Hey guys, this video will be titled Tritium, Organically Bound Tritium, Hydrogen. But to talk about those, we must talk about covalent bonds. As we've discussed in past videos, that tritium becomes bonded to carbon in the metabolic process when it is taken up in plant life, like vegetables and fruits, grains, wheats, etc. That tritium becomes bonded to the carbon inside that plant life. And when we eat it, it causes the biological half-life of tritium inside our bodies to drastically increase to something that we don't know yet. Tritium is said to pass through the body, the biological half-life, within 12 to 30 days. But that's under the assumption that tritium is never bonded and causing damage as it decays, as it beta decays and releases a beta particle and a gamma photon of energy that is closer than 0.56 nanometers from your cells. This is how it causes damage. Gamma travels at least up to 10 feet, around 10 feet, around. And the beta, the tritium, that's 0.56, which is, once it's bonded, it's definitely closer than 0.56. So covalent bonds. Importance of covalent bonds. Covalent bonds are the strongest bonds in nature and under normal biological conditions have to be broken with the help of enzymes. This is due to even sharing of electrons between the bonded atoms and is with anything equally shared. There is no conflict to weaken the arrangement. There are two types of covalent bonds. Nonpolar, possess no charge, and polar, possess a charge. Nonpolar covalent bonds. These are very strong bonds. The electrons in the adjacent atoms are shared equally, which means that there is no push or pull effect, dipole moment. This is the dipole I talked about in quantum mechanics. The Casimir effect, van der Waals forces, dipole, angular momentum, and magnetic moment. Okay? Example of relevance of pharmacology. Covalent bonds are found in protein chains where two sulfurs are joined together. In antibody molecules, this bond firmly holds the two parts of the antibody together, allowing the rest of the structure to hinge around it. Okay. Found this one too. I think it opens up the area of carbon-hydrogen functionalization to another level. An expert in borylation chemistry in the University of Bristol, UK, who wasn't involved in the work. Many carbon and hydrogen functionalization catalysts work on a molecule's most reactive bonds, while others need a directing group to guide it to a specific position. Back in 2000, Hartwig's team found a catalyst that preferred primary carbon-hydrogen bonds above all others. However, the reaction required a huge excess of the substrate, which is impractical if the compound is expensive or the product of a lengthy synthesis. Okay? Now the chemists design an iridium catalyst that borylates the most stable, least reactive aliphatic carbon and hydrogen bonds in a molecule. The catalyst reaction rate is almost 2 orders of magnitude higher than that of similar catalysts, which allowed the team to use only one equivalent of the substrate for the first time. Tritium, H3O, tritiated water. H2 water that neutron captures and is transformed into an H3O. All these safety limits, all these standards, everything must be reset. Look up radiocolloids. These are radionuclides that are bonded to other things. Wake up, people. Get educated. Comment down below your thoughts. And thank you for watching. I appreciate it. Thanks, guys. Bye.